Students from homeworks. So I think as of right now, we've assigned up through 138. So if anybody has any questions up through 138, we'll start there. Yeah, Jax. Yeah, man, no worries. You're good. Anybody? Questions? Anything we've done so far? Jackson, is that a hand or are you just chilling? Just chilling. Okay, keep on staying cool. Okay, well, if you guys change your mind, we can always catch up on the flip side. No big deal. Let's, knock this out of the park here, right? So, that's embarrassing.
It happens every year. I keep saying it. Like, it always happens.
All right. Today in section 15.5, let's focus here, folks. We're going to talk about financial mathematics. One of the areas in particular that we're going to be interested in is the idea of interest. So there's really two types of interest. And when we say interest, does that mean something that like fascinates us?
No.
No. In finance, what are we talking about?
Money over.
It's like the money the bank pays you to keep your money in the bank, or the money a bank charges you for borrowing money from the bank, right? Everybody cool with that? So interest kind of works both ways. In general, how does a bank make money?
Borrowing or lending.
They're going to take your money and lend it out at a higher interest rate than they're paying you, right? That's essentially what's going on. So the interest rate they pay you to keep your money in the bank is less than the interest rate they charge someone to loan their or to borrow that money. You know what I mean?
Yeah.
That's ostensibly how the bank is making money. I mean, there's other ways too, but like that's the most basic principle. All right. In the two types of interest, the first one, or the first type, we call simple interest. So in simple interest, the amount being paid is based on, or based only on, the initial deposit. So I got some equations here. Let's define what these terms mean. So FV is like the future value for the account. The PV is like the present value. R is the interest rate. And again, we represent that as a percentage. N is the number of years. And then cap I is the amount of interest earned. And notice that I give you guys two ways to calculate cap I, that amount of interest earned. You can calculate it directly, or if you've done the first part, obviously the difference between the future value and the present value is going to be the interest that's been earned, right? So depending on how the questions have been phrased and what you've already done, one or the other might be more convenient for you to do. You know what I mean? Let's do an example. Say you invest $2,000 at a 6% interest rate. How much money do you have in the account after 3 years? So it's asking for a future value. Right? So we're going to be solving for FV. What's going to be going in for PV? The present value. The 2,000, right? The amount you initially put into the bank. And what's going to go in for the R? The 6%. And what's going in for the N? 3 years. And so then we just grab our old friend, Kelky McKelkerson, and just kind of type this guy in as it appears. I'm going to use the fraction command here. That's a little bit of overkill since there's only one number in the denominator. You don't really need to use the fraction command, but I'm going to do it anyways. So I get $2,360. How much money did I then earn in interest? 360 bucks. Everybody cool with that? Okay. In reality, this is not the way that most financial institutions pay interest, because it's kind of a ripoff. Why? Because the actual account value isn't the number used when they compute the interest. Right after the first year, you'd have 2120 in your account. So the interest you earn in the second year should be based on that number, not the 2,000. Everybody kind of see where I'm going with that? When we compute interest that way, where the current account value is what you're earning interest from each time the interest accrues, that's called compound interest. So our formula there is FV equals PV times 1 plus R over 100K to the NK. So the FV, PV, R, and N are still mean the same thing, so I'm not going to rewrite what those are. Is that okay? The K, though, is new. The K is just going to be the number of compounds per year. Now, I'm guessing that most of us have a bank account, right? Probably a lot of us have part-time jobs and we got to put our money somewhere. Have you ever looked at your bank statements that you get from the bank? Okay. So if you had, you'd notice that your interest gets paid more than once a year. Most banks pay interest quarterly, so you probably get an interest payment 4 times a year. So when we talk about the number of compounds per year, most savings accounts, the interest is compounded quarterly because it's paying out 4 times during the year. Everybody's okay with that idea? Now, it's not paying the full interest rate 4 times a year. It's paying 25% of your interest each of those 4 times. So that's a common. So basically what I'm saying there is that value for K is always going to be kind of expressed in words. So you actually have to read the problem pretty carefully in order to make sure that you're identifying the actual value for K. Let's do an example. If you invest $2,000 at 6% interest rate, at a 6% interest rate compounded annually, how much money do you have in the account after 3 years? And then how much did you gain in interest? Now, this reads almost identical to the previous question, right? There's two words, importantly, that are differing. They are compounded annually. When I hear compounded, I know that I should be using the compound interest formula. That's convenient that they've named it the same way. Everybody's cool with that? Again, we're asking how much after 3 years. That's going to be a future value. So we're solving for FV again. What's the value for, what are we putting in for PV? 2,000. What's going in for R? What's going in for N? 3. And then what's going to go in for K? Yeah, the annually is telling me that one time per year we're calculating interest. Okay, so calculator time. Oops. What did I do? Anybody see?
You didn't do it to the power.
Yeah, I didn't put it in the exponent. Yeah. Okay, so this time we got $2,382.03. So if I compare what we got from simple interest to compound interest, small deal, medium deal, or big deal? Yeah, small difference, right? Not much of a difference. Everybody agree? What is it? It's like $20 or some $22, which is like, yeah, that's $22 over 3 years. You know, like I missed one Chipotle meal or something. Not that big of a deal. What if we instead extended this out to 30 years? Let's look at what the difference would become there. So I'll change the 3s to 30. So with the simple interest, I get $5,600. And with the compound interest, I end up with $11,486. Big deal, medium deal, or little deal here? That's a big deal, right? Like almost a $6,000 difference. I'd be pretty peeved if I lost out on $6,000. That's a lot of trips to Chipotle. So many burritos. All right. So why the big difference? In the simple interest, you're earning $120 every year. That's it. The compound interest, you're earning based on the current account value. So in year 2, you're earning on the 2120. In year 3, you're earning on the next one, and year 4. So every time you do that, the account value is a little bit higher, you earn a little bit more interest, and all that piles up in quite an impressive way. Or probably the more effective way of thinking about it is from a function standpoint. So what kind of function is simple interest? It's a linear function, right? You're getting the same amount changed every year. It's like a constant slope. Everybody agree? And compound interest is like an exponential function. And you see that as time goes by, that exponential function grows way faster than the linear function. So you're getting way more bang for your buck, particularly as time goes on. You know what I mean? So that's kind of, from a mathematics standpoint, what's going on and why there's such a big difference, right? Okay, let's talk about the effect of K, right? Because that's the thing that's really kind of the parameter that's different between the two. So we've established that annual implies that K is equal to 1. What would semi-annual mean? 2? How about quarterly? 4. What about weekly or monthly? Yeah. Weekly, 52. Daily, 365. Maybe I should mention biweekly here. What would biweekly be? 26. Why would that be something worth mentioning? Yeah, we get paid every other week, right? We get biweekly pay. So that is oftentimes a financial time period that people would be interested in. So let's just take this original problem that we worked on. So when it was annually, we got 2,382 bucks. If I change that now to semi-annually, I'm just going to replace the 1s with 2s. You think it's going to be small change, medium change, big change? Let's see. About $6. Call it small, right? So we've gone up to 2388. Changing it to semi. What if we change this to quarterly? So we got about $6 difference. Do you think it's going to be more or less than the 6? More? Let's see. Went up, got $3 improvement. Okay. Well, let's change that to monthly then. I'm going to change that 4 to a 12. That's got to make a big difference, right? It's 3 times as big. Let's see. $2. Okay, well, let's go to 52. Go to a weekly. Less than $1, like 80 cents or something. Oh boy, Mr. Kulik. And if we do this daily, $0.21. So what are we seeing? That as that value for K goes up, the improvement in your earnings is kind of decreasing each time, right? It's still, I mean, a bigger K is better, period. But the bigger it gets, the less effect it is having. You know what I mean? So that being said, what if we have it compounding continuously? That basically at every instant, we're earning interest. What would that imply K is? Infinite. Yeah. So let's just imagine that we have this case. And let's see what happens. So we're going to be looking at this, right? Everybody cool? So far, so good? All right, I'm going to do one sneaky thing here. Well, maybe I'll do more than one sneaky thing. But the first sneaky thing I'm going to do is rewrite that exponent, nk, as 100k over r times nr over 100. And you might say, Mr. Kulik, why in God's name are you doing that? Well, if you look at those two fractions, when I multiply them together, I'm still getting nk. Right? Everybody agree? So it's still the same thing. And you're going to see why I did that in a moment. But I just want to make sure we're clear that this is still the same thing that we had before, right? Now I'm going to make a clever substitution. So I'm going to say let 100k over r equal x. So if 100k over r is equal to x, what's r over 100k equal? The reciprocal, so 1 over x, right? Everybody's cool with that? And then I have 100k over r, so that's going to be my x. And I'm going to just write this as an exponent of an exponent since it's being multiplied. It's the same thing. Everybody's cool? Who recognizes this? Anybody? Let's go back to the very first lesson here. Oh, maybe it was going to be the second lesson. Let me double check here. Nope. There it is. Look at that. The limit as x approaches infinity of 1 plus 1 over x is equal to e. Right? So if we go back here, I know that 1 plus 1 over x to the x is what I have here. And if k goes to infinity, I know that 100k over r is also going to be going to infinity, right? And if 100k over r goes to infinity, then x is going to infinity. Everybody buy that reasoning? Since the infinity is in the numerator of the fraction. So what can I replace that stuff in yellow by? E. So I have a new formula for continuously compounding interest. And I'm not going to define any of the PV, FV, N, or R because they're still the same, mean the same thing as the previous ones. Everybody's okay with me doing that? So this is our third now interest formula that we have, right? We have simple interest, compound interest, and now continuously compounding interest. Okay. Says Jack invests $800 into a savings account with 5% annual interest rate. compounded continuously. How long will it take for Jack to have $500 in interest? What two words in this am I most interested in initially? Yeah, compounded continuously, because that tells me the formula I need to use. Right? I have 3 formulas to choose from now, so I have to make sure that I'm reading the question carefully and picking the right one, because all the questions sound kind of the same. But I think we've done a good job of identifying the key words we're looking for, right? Okay. What are we solving for? Yeah, because it says how long, so we're going to be looking for n. Great, so let's start filling things in. Where does the 800 go? That's my PV. Great. And where's the 5 go? R. Is there a pirate in the room? And then what do I do with the 500? It is not the FV. Yeah, so the future value is going to be 800 plus 500. Since it asks for when will we have earned $500 in interest, that's going to be on top of our account value is going to be the initial plus the interest, right? So now we're just going to solve for n. Great. What's my first step? Divide by 800. I'm going to reduce at the same time. Is everybody okay with that? And I'm going to just reduce that fraction. 5 over 100 is 1 over 20. Everybody's cool? Next step. What? Yes, so you're going to take the natural log of both sides. We're going to use a logarithm because our variable is located in the exponent. And why did we choose the natural log? Yeah, that natural log is log base e, and we want to pick the logarithm to match the base of the exponential, e in this case. All right, and my last step would be to multiply both sides by 20. And then it's just calculator time, my dudes. Where is my mouse? Where is my mouse? I have the 2 screens going. And sometimes I just like lose my mouse. Like I can't find where the pointer is. And part of that, like OneNote makes it very hard because with your mouse, if it's in drawing mode, your mouse is just like a little dot. And it's like, couldn't you have made it look like a pencil or something, the pointer? So it's just like, oh, it's easier to find if it just looks like a, like a hand with a pencil in it or something instead of just like a tiny red dot. How do you feel on that? Everybody cool still? Again, so far this has been very plug and chuggy, right? No skills different than the solving have we applied. We just have some new definitions or a little bit of vocabulary, but not very different than the previous sections. Let's look at a different kind of example here. Say we're asked, or can I say, you find an account that has a 6.5 annual interest rate compounded monthly. What would the equivalent interest rate be for an account that is compounded annually? Oh my. Something's funny. Okay. So everybody's cool with why we use the normal compound interest formula, right? Okay. So in our monthly formula, what can we fill in? What values can we fill in? R and K. All right, so let's fill that in. Everybody's okay with that? Now, what I realize here is that I can rearrange this in kind of a clever way. So I can do that, right? No big deal. What I did there, right? We just use the exponent of an exponent property. What I'm going to do now is I'm going to take that stuff on the inside and type that into my calculator. So I get what, about 1.067? Oops. Still doing okay? Now take a look at where we're at with our monthly equation and where we're at with our annual equation. Everything other than the stuff inside the parentheses, oh, excuse me. Well, we should do this, right? What can we say about the annual? K is 1. There we go. Whoop. So I can say that. Those two things have to be the same. Everybody agree? Since everything else in the equations are the exact same? So if I subtract 1 and multiply by 100, I get 6.7%. Now, this process that we've just done here is super common in financials, because what it does is it creates a good way to compare two different deals, right? Like if I have, this thing that's at this percent compounded this way versus this thing at some other percent compounded a different way, like how do I know which one is better? I convert them both into like an annual interest rate, and then I can compare whichever one is bigger. We actually have a name for this. This is called the annual percentage yield. Or APY. This is just the conversion to an annual interest rate. So I take whatever your interest rate compounded however you want, and I convert it to a new interest rate compounded annually. And we're going to take that process that we did there, And we can streamline that a little bit so that it's just like a formula. So this formula that I've written up here is just the process that we've used above. I just formularized it. And let's do a little example then. So it says, which savings account is the better investment? One that pays 7.8% interest compounded quarterly, or one that pays 7.65% interest compounded weekly? Anybody with an initial guess? Just on their gut? That's all we're doing right now is guessing.
Yes.
You think the first one's going to be better? Okay, let's see. So what we're going to do is just convert those both into APYs. You think it's going to be the other one, Mackenzie? Okay. Yeah, no, I don't blame you. So I'm just going to write them both down straight away, and then we'll type them both into the calculator at the same time. And I'm going to use the fraction command here and write this out. Instead of writing like 400, I'm going to write 100 times 4, mostly so that I can go back and save the same editing or use the same thing I typed in. So the first one is about an 8.03% interest rate. Cool. So we'll change the 8 to a 50, or the 4s to 52s. And then the 7.8 to 7.65. And that's a 9.4%. So which one would be the better investment? The big one that's bigger. In this case, the first one. Mackenzie, you're wrong. But we're just guessing, so who the heck knew, right? It was 50-50. Because we didn't really have anything other than like maybe some instinct. Everybody's feeling okay with this idea of APY? It just basically gives you an easy way to compare, loan options or investment opportunities or whatever. Okay. Next thing we're going to define is something called an annuity. Oops. There we go. That's how you spell it. And this is an account into which a sequence of payments are made. And we say we have an ordinary annuity let's just say that's an annuity where all the payments are the same size. So what does that ordinary annuity sound like? What kind of financial things sound like our ordinary annuity? So, all right, kind of like a paycheck. Sure. How about a retirement savings account? Right? If you're saving for retirement, typically you're going to take the same amount of every paycheck and just kind of save it for retirement. What else? Think about going the other direction. Sure, like a saving for a college fund. Yeah, very similar to the type of thing you do for retirement savings. How about a loan? It's going the other direction, but the loan, you're making regular payments to the bank, right? And there's some account that the bank is putting those in until it gets to even. You keep paying. Everybody agree with that? So these annuities are frequently used in loans and also like, savings accounts or investments, right? Are the two places this kind of comes up. So our annuity equation, or our ordinary annuity equation, I should be specific. In this class, we won't look at anything other than ordinary annuities, and like, goodness gracious, that's the majority of annuities are regular or ordinary annuities where you're just doing the same thing over and over and over again. It's a pain in the tuchus to deal with something else like, oh yeah, I saved $35 this week, and then I saved $120 the next week, and then I'm going to save, where you're just like, who knows what you're saving? Like, really hard to make a prediction about that. So this is our annuity formula. Now there's 3 new letters in here, right, that we need to define. So let's do that. This is the regular payment. So that's the payment size. Actually, let's just call it the payment size. So like $100 a month or whatever. I is actually another formula. I is R over 100K. And cap N is also another formula. It's NK. And now we already know what little r, little k, and little n are, so I'm not going to define those again. They're the same things they have been throughout. So we're just basically using these so that our formula doesn't look quite so terrible. Everybody's okay with that? All right, let's do an example then. At the end of each quarter, Sarah makes a $500 payment into an annuity account. If her investments earn 7.88% interest compounded quarterly, what will the value of Sarah's annuity be in 20 years? Well, I heard the word annuity in here. So not surprisingly then, I'm going to use my annuity equation. Everybody's cool with that? What are we going to be solving for? Which letters or letter? What is that? It's a future value, right? The value of the account 20 years later, it's a future value. Pretty, hopefully that's pretty obvious. Okay. All right, so let's go through here. What is the 500? That's my R. Okay. Now, I'm just going to write the rest of this stuff here, and I'm just going to write next to it the value for I. I guess maybe I'll write over here. I'll do this also, so it's all in the same place. Okay. Where's the 7.88 go? That goes in for R. And then what's the K? Yeah. So it says quarterly, so the K is 4. And what's my N then? $20. Okay. So it's calculator time now, my dudes. Yeah, of course, man. And this is one where you definitely would want to use your fraction command. So I'm going to have 1 plus, and then I'm going to use the fraction command again to type in my I. Oops. Now I'll use the fraction command again to type in my I. Probably should have typed in I and stored it as a variable. That would have been smarter, Mr. Gulick. So I do that and I get $95,483.39. Woo! I'm rich. Everybody's cool with that? Now, when we started talking about annuities, we talked about how we can think about an investment as an annuity like this, or we could think about like a loan as an annuity, right? So this is our annuity formula for a loan. Everything here is the same, except now we have this PV. Can somebody grab the door for me? Paul managed to kick the doorstop out. Hey, can you put that doorstop back so that it doesn't shut you out? That's okay. It's a pretty Paul thing to do.
Sitting there just left my tablet somewhere. I don't even know where. I had it during morale. So.
Oh, it's in the scroll.
I thought you just meant you left it at home.
Yeah, that's
No, I left some of the things at work. So.
Yeah, it does make it worse. All right. So here, when we say PV, what we're talking about is not a present value, although you could think about it that way. I would think about it as like a principal value. When you talk about a principal, what does that mean? In regard to a loan? It's how much you borrowed, right? It's how much money you borrowed. Or if you think about it in the terms of present value, when you initially take the loan out, say you get a loan for $10,000, okay? How much money do you have initially? $10,000. Or a $10,000 debt, and then you're paying that down every month, right? Okay. Let's look at an example. So I have like 2 more examples here, my dudes, and then we're donezos. Sound good? Yeah, I thought you might like that. All right. Maria buys a new car for $18,500. What are the monthly payments for a 4-year loan if she makes a $2,000 down payment and the annual interest rate is 2.9? Well, hopefully, because it says right in the problem that we're taking a loan that we would go straight to our loan formula. So what are we solving for in this loan formula? Which letters? Yeah, what are the monthly payments? So that's going to be R. Are going to be our monthly payments. Okay. So let's start filling in some values. What are we gonna put in for PV?
18,000.
Not 18,500.
Oh, sorry.
Not 2,000. 16,500. Right?
Oh.
So again, this is a little bit of an unfair question because probably none of you guys have bought a car by yourself. But what typically happens is you walk into your car dealership or whatever, and you agree to pay some money up front. That's called the down payment. And then you borrow whatever other money you need in order to take the car home. Oh, I shouldn't have written all that stuff there. Anyways, that's fine. So let's fill in the I. The I is R over 100K. What's my I? Or my R? 2.9. And then what's the K here? 12, right? We're making a payment every month. And then what's my little n? 4. Okay. So then I'm just going to divide both sides by all of this stuff. And that's going to give me my value for R. Everybody cool? So this one, I'm definitely going to abuse the heck out of that fraction option on my calculator. So I'm going to do the fraction command and do my 16,500. And in the denominator, I'm going to do the fraction command again. I'll do 1 minus, 1 plus, and then where I is, I'm going to do the fraction command again. 2.9 over 100 times 12 to the 12 times 4. And then over I again. So fraction command again. 2.9 over 100 times 12. Oh, Boise. Oh, I see what I did. Anybody see what I did? Forgot my negative sign. There we go. So I get $364.49. Now, needless to say, if you look at what I typed into my calculator, is this something you probably want to practice a little bit? Just making sure you feel comfortable getting that into your calculator and getting the right answers to come out. It takes a little bit of practice. It's not that hard, but the fraction command makes this tremendously easier than it used to before that was nicely available. If you have a really old calculator that doesn't have that option, I feel sorry for you because the parentheses get pretty terrible. But use the fraction command, makes life pretty doable. I have one more question, or one more example, and then we're going to call her quits for today. Yay, quitting. I'm a natural born quitter. All right. It says, using the same information from example 39, that's the previous, and assuming all of Maria's payments are equal, how much interest does Maria pay over the life of her loan? So what I'm going to do is I'm going to calculate our total costs. So what's everything that Maria pays for the car? We pay the $2,000 initially, right? And then we pay $364.49. How often do we pay that? Every month. And how long? For 4 years. Huh? Yeah. I wrote 4. Did I not say 4? Oh, don't get confused, because you're confusing me now. So if I type that all into my calculator, I get $19,495. And then some cents. What was the cents? 41 cents. Everybody's okay with that? So the interest is going to be the total cost minus the amount borrowed. Oh, no, not that. It'd be just the price. So that's going to be the 19,495.41 minus the 18,500. So $995.41. Almost $1,000 the bank made offer. What do you guys think? You know, it is what it is, right? All right, well, at this point, we can finish out the problem set. So notice that for Sunday, the problem set is just up to 130, right? For this week, just up to 130. Next week's goes 131 to 184. This finished chapter 5. So what are we going to do next class? Review day. So it'll be just like a work day to get stuff done. And then what's going to be the class after that? Test. So we're probably looking Wednesday next week, I think, for the test. If that looks like a particularly terrible day, we can negotiate on Monday maybe a different test day. Okay? So just kind of let's table that till then, but tentatively that's what we're looking at is a Wednesday test day.
I like pretty testing.
So I get that, but what that also means if